So I have this example of a car cabinet thermostat, or car cabin, not a cabinet. But when you're in the car during summer and it's really hot when you get into the car, you want to cool it down as fast as possible to a nice cool temperature. You might have seen these dials in the car that you control the fan speed from, for example, from 1 to 4. You can set it somewhere. For some dumb reason here it's set to 2.5. I'm pretty sure that's not possible in your actual car. But let's say that you think that if you put the fan speed to 2, then you assume that it will get to the right temperature over time. But as we see in this graph over here, let's say that the temperature at the moment is like 34 degrees. It's really hot inside the car. And if you just set the dial to 2, it will take quite a long time. This says time in minutes. My headshot is in the way of you seeing, but it's in minutes. And so, even though that doesn't really matter, so it will take quite a long time, and it might not even reach the 21 degrees because the sort of the difference that it makes with this certain power to the temperature of the cabin is not as much when the difference between the reference temperature, so the target temperature, and the actual temperature gets smaller. So it would need more power to actually reach a cooler temperature. So what we see here is that you have some sort of a estimate or guess, or one could say a guesstimate of what is the correct fan power to achieve this reference temperature in your car cabin. And this is called open loop control. And it's usually slow and it can be quite inaccurate. Then, if we compare to another approach where you're the controller here, and at first you turn up the fan to max setting, max power, and the problem then is that it gets cool much faster, but it gets the temperature gets below the reference temperature, so you need to then switch it to a slower speed, slower fan speed. But then the problem again is that then the car cabin is hotter than we want. So then you need to adjust little by little, and in the end it seems that actually the setting 2 could be the one that keeps it somewhat in the reference temperature. Most likely you would need to change it every now and then to setting 3. But what I'm trying to demonstrate here is that here you act as the controller of the system as a person. But if we're talking about autonomous control, then we have a system that we set a target and it knows the reference value. Sorry, reference value is the target value that we want to get into. Then we have the actual value, which is this blue line. And the thing that the controller tries to do is to minimize the error. So the difference between the reference and the actual value, or temperature in this case. And so rather than you having to be there and switch the fan power all the time, you could have a controller to do that for you. So this is the control system that we had in this example. So the input to the system is fan speed, the thing that we can control. Then the system is usually called a plant in control system terminology, and that's the cabin. And then the output of this system is the temperature that we try to control with our input. And before we go forward, I would like to set straight some terminology for you guys so that we're talking about the same things, and these are quite standard names for all of these phenomena regarding control, so they will be useful in other contexts as well as this course. So rise time is over here, so it's the time that it takes from the start of the control to reach the reference value. So the rise time reflects the aggressiveness of the controller, how fast it reaches to the target value or the reference. And then we have overshoot, is the amount of how much the actual value surpasses the reference value. So if you have a huge overshoot, it might lead to a lot of this sort of oscillating phenomena, and also there might be cases where overshoot is not allowed at all. So then most likely you need to have a slower rise time just to keep it under control. And then there's these, I have planted these links, or if you click this figure, download the slides, you can go and study further on these terms. Okay, then there's peak time, and that's the time to reach the highest value of the control, so the maximum overshoot. Continuing on the terminology, steady state error. What is it? Well, we could first define what is steady state. It's when the actual system is very close to the reference value set for the controller. But however, in real life, we don't need to achieve the exact reference value. It's good enough when it's close enough. So here are these tolerance limits defined like a higher and a lower value, and if the system is continuously within those limits, it's called that the system is steady. However, then there is always this steady state error. As I said, it never reaches the actual reference value. So this steady state error is a measure of how close we are to the reference value, even though we clearly see that the system is now following the reference. Then settling time. It's the time to reach this steady state, actually not steady state error, but to reach steady state. So here we have reached the tolerance limits or a steady state in this time TS. The text is behind my video feed, but believe me, it's there. And yeah, so in one sense, you can measure how fast your system reaches the target value or reference value by rise time, but that does not tell if the system is steady at that point. If you want to really know how long does it take from activating your control to actually reach a place or a time where the system is following the target, the reference value that it's given, that's settling time. Okay, I already talked about this a bit. So we have two different kind of systems. Open loop system, where you don't get any feedback. So in the car cabin example, you don't know what is the measurement, what is the actual temperature at the moment. You only try to guess based on system physics that are known beforehand, that what is a good control value. Then you can still you could change the value based on some sort of a model. So in this case, like the fan speed, you could still change it based on some calculation, but you don't know what is the actual value, what is the actual temperature at the moment in the car cabin at a certain time. And then you have closed loop system that is much more accurate, and so there is measurement, there is a temperature sensor, and you know what the temperature is at the moment, and then you compare the reference value and the actual value. You get an error in between those two, and then based on that error, control input to change the output. So control the fan speed to change the temperature of the car. Here are also schematics of those two. We already saw this open loop controller before. And then if we look at the closed loop system, it's quite similar. So you sort of have this same open loop system here. This is the same block. The thing you add is that you're getting feedback from the output temperature, and then you take the difference between the reference, so let's say the 21 degrees Celsius, and the actual temperature that is currently in the car cabin. You take that error and you feed it to a controller, and based on that the controller controls the actuator in this case, or the input, the fan speed. And if we put this to a vehicle speed controller context, because we will be talking about longitudinal controllers next, is that the input here is the gas pedal, the system is a vehicle, and the output is the speed of the vehicle. And if we look at the feedback closed loop controller, we measure the speed, we see what's the difference between the speed that we want to have and what's the current speed, feed that error to a controller, and based on that control the gas of the car. Okay, that concludes the first part of this lecture.